Hello everyone, today we're going to talk about the application of Feynman technique and Euler's rules in the real applications. It's about how we use it to solve like this equation. It is rather tricky because this integral is kind of improper. So these two methods is what we're going to use today. And now we move on the equation itself. Like just take a glance, we found this x of the denominator is very, very annoying. So we want to remove the x out of the equation and we can find this infinity integral, right? So how about we use Feynman technique to set a function? We can set a function a, fa, times e power of a dx, e power of ax times dx. So in this case, when a equals 0, the function gonna be infinity integral 0 to positive infinity, and sine x over x e of power 0 times x times dx, and the function will be the original function that you want to find. Yes. So why I would like to choose this e power of ax and choose the parameter a, because if we take derivative of this function, right, they're gonna be x times e power of ax, which means there's an x in this equation, and we can eliminate the x, the denominator of x. So we take the derivative of the function of a, which means we just need to take the derivative of the inner function, or we said the inner equation. As we take the differentiation of the whole equation, it just means to take the differentiation of the inner equation, right? So in this case, it will be sine x times e power of ax times dx, right? And only if the original function fa, when a is 0, is the value what we like to find. Is the value what we find, right? So now we're gonna take the differentiation of the function, and as this equation is easy to solve, and after that we're gonna take the integral of the differentiation to find the original function, and we take the 0 to the fa to find the value of f. So this equation we can use. Now we're gonna use Euler's rule. As we know that Euler's rule is that e power of ix equals cosine x plus I times sine x, right? So we can rewrite this equation as so this sine x is the imaginary part of this complex number, right? So we can rewrite this function x e ix times e ax. Now we're gonna find the imaginary part of the equation. Now simplify this equation. Is I plus a times x of power and after that we're gonna move on to find the value of this integral, right? And for the primary integral rules, we can know that this is equals to the imaginary part of I plus 1 over I plus a times e power of I plus a times x from 0 to positive infinity, right? It seems that we lost dx. Oh, it's my fault. Yeah. We lost dx. We lost dx. That's a small mistake. Never mind. Because this integral is with respect to s, right? We should remember that. That is very essential. That is for when x is positive infinity, take it into this equation, and when x is 0, take it into this equation, and for the a here is smaller than 0. But why? But why is a is negative? Because when we use the Feynman technique, we should ensure that the function, the original function, is equals to the integral of the derivative differentiation function, right? So when we use Feynman's technique, we should ensure that the former equation and the equation we set, that is both convergent. So as the graph of e power x is like this, right? E power x, and when x approach to positive infinity, this function is not convergent. Not convergent. So we can transfer this function to e negative x, right? After that, the graph of the function will be like this. So when x approach to positive infinity, this function will approach to 0. So use this idea. When we when we set the parameter a, it should be negative, and so that the eax for this equation, when x approach to positive infinity, this equation approaches to 0, right? And we know the a is smaller, it's negative. The parameter a is negative. So when x is positive infinity, this, no matter how the x value would be, because e power ax is approached to 0, so the e power ax times e power ix is also approached to 0, right? Because anything times 0 is 0, so this is approached to 0. So this function will be like the imaginary part of, and because when when x approaches positive infinity, and the whole equation is 0, so take 0, and minus when x is 0. So when x is 0, we can actually find that the equation is 1, because E0 is 1, right? 1 plus 1 over I plus a. So this is 1 over I plus a. And to find the imaginary part is, so we need to simplify the equation. Like this is a square of a plus 1 over a plus I, right? So this is the imaginary of the complex number is 1 over a squared plus 1. Now we eventually find the value of the derivative of fa. Now don't forget, we want to find what? We want to find the f is when the a is 0. So is the things we want to find, right? So now we're gonna take the integral of the differentiation of a, right? Because we want to find the function. So we take the integral of 1 over a squared plus 1 dA. That's equals to arctangent a, right? Plus a constant, this is constant c. But now we're gonna solve this constant because we don't know the value of c, right? But how can we solve this? As a is negative, we can see the former function fa. When a approaches to negative infinity, right? When a approaches negative infinity, this one will be 0. Will be 0 times a bunch of things, and the whole things will be 0, right? When a means when a is approached to a negative infinity, right? So when a is when a approaches to negative infinity, so this is negative infinity, this is a negative infinity, right? We will easily find that the differentiation of this function is arctangent a equals f. This is negative infinity. Oh, this is the differentiation. So now we take the integral of the function. We'll find that arctangent a plus c, right? Oh, forget the a. Never mind. This is the fa function. So when a approaches to negative infinity, this will be 0. And this will be minus pi over 2. And thus, therefore, and c is pi over 2. So the function is fa equals arctangent a and plus pi over 2. The value we initially wanted to find is the value that we want to find is when a is 0, right? So it is arctangent 0 plus pi over 2. As we know, the graph of arctangent is like this. This one approach to pi over 2. This one approach to negative pi over 2. So when arctangent is 0, so the value is 0. So eventually, so f0 is pi over 2. So this equation is equal to pi over 2.